So actually what was happening, the linear law reflects the inability or more accurately the futility of either side to mass its forces effectively. Lancaster referred to this as a characteristic of ancient war. That like in ancient times, there were battle between the two parties. Let us say here we have considered a blue army and a red army. So in olden times, when weapons directly answered weapons, the act of defense was positive and direct. The blow of sword or battle axe was parried by sword and shield. Under such conditions, it was not possible by any strategic plan or tactical maneuver to bring other than equal number of men into the actual fighting line. So one man would ordinarily find himself opposed to one man. So this is what is depicted in this diagram or in this figure also. Like we are having two different armies, and we are going to study a battle between the two. Say we are having blue army and we are having red army. So we will see that how it would be studied with the help of a mathematical model. And there were also certain assumptions that in this situation both the armies have equal fighting skills. Each army will engage equal number of units at a time and would go on like this until smaller army is wiped out. So in such cases, attrition depends solely on the effectiveness of the individual combatant. So these are two armies, and we can see that 5 men from blue army and 5 from the red army, they are engaged in the war. So it is just represented with the help of this rectangular frame in yellow. So it is showing that from both the armies, equal number of men are involved in the battle when it is started. Okay. So let us try to understand its mathematical concept. Suppose red and blue forces are engaged in the combat, and that is represented with the help of capital R and capital blue. And small t is representing the time. Both the forces are unaimed fire and targets remain constant, and we can write the corresponding mathematical model given by these two equations. Assuming the death rates are proportional to the product of size of the two armies. So here a small r and small b, they are the fighting effectiveness of each combatant. That is the attrition rate actually. So the attrition rate is the rate at which one surviving combatant destroys the opponent. And like we need to solve this equation, we need some initial conditions to evaluate the constant in terms of mathematics. So these are our initial conditions, that is R0, that is the initial army men available when we started the battle, the when T was 0. Time is not yet started. So initial availability of the red and armies are not B0. So we know how to solve it, and when we solve it using our basic techniques, we reach to this expression of the form 4. So this is called Lancaster's linear law. So it will help us that under what conditions who will win. So this is all given by the equation number 4. Now we will see that what will happen if is the final time, or if we think that blue force will win. So what will happen? For blue force to win, since it is talking about the ancient wars when some restrictions were there, then we say that blue army will win. That means it has eliminated the red army. No number of army men from red army are left over. So only BT is left. Then we say that blue army has won the war. And if we will put R is equal to 0, then we got this expression for B. So using just we rearrange these terms, and we reach to this conclusion, that is, for blue force to win, effectiveness ratio need to exceed the initial force ratio. This is our initial force ratio, R naught, V naught, and this is our effectiveness ratio that was given by the attrition rates of Red and Blue Army. So this ratio, when this is greater than the initial force ratio, then we will say that our Blue Army is winning. And similarly, if we claim or if we say that under what circumstances red force will win, then similarly, if red force is winning, that means when battle ends, there are some number of army men left from red army and blue army is totally eliminated. And similarly, if we will put this B is equal to 0 in our previous expression, we reach to this equation that, and we rearrange the terms, we get this ratio. So here it is B upon R, and here we are getting R upon B. So thus for any of them to win, whether red army win or blue army win, the effectiveness ratio need to exceed the initial force ratio. This would be the conclusion from these two expressions. And there may be a situation that none of them wins, there is draw. That is when there would be not be any survivor from blue army and red army. Then both are 0. When B is 0, R is 0, then these two ratios would be equal. That is, both forces get annihilated and battle comes to draw. Okay. So, but there were some certain limitations of this linear law. So that's why to overcome these limitations and to be more focusing on the modern warfare, the second law was given by Lancaster. That was the Lancaster's square law. So first we need to understand what was the difference between the Lancaster's linear law and square law. The first foremost difference was that the linear law was based on the ancient combat and the square law was based on the modern combat. And in case of linear law, one target at a time, as we saw in the diagram, that when blue and red armies were engaged in the war, the equal number of men were from both the parties, and there was one-to-one war between the two armies. One army man from blue army is competing with the one element of the red army. So there was one-to-one combat. But it is not so in case of Lancaster's square law. So let us see what it says. The restriction established by the linear law is now lifted. So now any combatant can engage any target in range and in turn receive fire from multiple enemies. Thus, every element can participate in every stage of the battle. So there is no more restriction of one-to-one engagement. So any number of men can attack on a particular focus also. So in addition to the homogeneity of the forces and aimed fire properties, it also assumes that forces are within weapon range of one another and the attrition coefficients are constant and known. So that means each side's losses are proportional to the currently surviving strengths of the opposition. So now let us see how this thing is modeled with the help of differential equations again. So here we have mathematical expression for this. So equation number 5 and equation number 6, capital R and capital B are representing the red and blue armies. So it means that instantaneous death rate experienced by a fighting group is equal to the product of the number of opponents and their individual fighting abilities. These are the fighting abilities, small b and small r. And this is the, since it is the rate of change of red army, so opponent is blue army here, and in case of blue army, opponent is the red army. So small b and small r again represent the attrition rates, that is the rate at which one surviving red combatant destroys the other combatant. So if we solve equation number 5 and 6, we get this expression in this form, that is 7. And these are the initial army men in red army and blue army. So this is called the Lancaster's square law. So it can predict the outcome of a combat if initial strengths and effectiveness constants of both the forces are known. So this model has several mechanistic interpretations in the literature also on human warfare, which assumes that armies are reduced according to the rate of incoming fire from opposing army. Later on, we will also see certain examples, and we will see how, if we are having some numerical values, how we can solve these models and we can draw the conclusions. So let us see what are the observations from the Lancaster square law. So, like we want to see that under what circumstances blue force will win or red force will win, then again we will solve it and we come to the conclusion that for blue force to win, relative effectiveness ratio of two forces must exceed the square of the initial force ratio. Similarly, if we want to see that when under what circumstances red force will win, then we will reach to this conclusion. And at this stage, when both forces get annihilated together, battle comes to draw, then they are equal. So let us see an example here where instantaneous death rates of two armies are given with attrition rates and initial strength. Suppose we are having these two differential equations and we know they are representing my battle, and we are having some initial strengths of red army and initial strength of blue army, that is 1500 and 900, let us see. Now our objective is to know who will win at what time. This is what we want to know from the given data that is given in the form of differential equations, where we are having the values of small r and small p. They were called the attrition rates. So we can answer these questions based on our study. So if we solve these equations, we get an expression of the form this R and B. So it can be observed that the value of blue army never touch 0. So it means blue army will not fully vanish. But since red army will touch 0 at some time, red army will be eliminated completely. And as a result, we declare that blue army wins. So to calculate the time in which red army is defeated and the losses sustained by both the sides, we put R is equal to 0, then we will get T as 0.6. So further, to find the losses sustained by the blue army at this time, we get B as 498. That is the number of soldiers lost by the blue army. And finally, at the end of the battle, blue army is left with 402 number of soldiers. This was you can say that numerical example. Actually, a similar type of famous battle is the Battle of Trafalgar, one of the best suitable example for this type of discussion. The Battle of Trafalgar was a naval engagement fought by the British Royal Navy against the combined fleets of the French and Spanish navies. So we can see in the figure that the ships in each fleet line up in a row. So these are the fleets. We can see the one is on this side and the other one is on this side. They are represented with the help of white and black colors. So they are sailing parallel to each other. We can see this one is sailing in this direction and parallel to this, the another one is sailing. Okay. So they are sailing parallel to their opponents and firing as they sail past each other. So these arrows, they are representing their firings. So this fleet is firing on the opponent, and this fleet is also firing on the opponent. So these arrows are representing the fires of each fleet on the opponent. So they repeated this maneuver until one fleet disabled or sank the other. So we can see that this firing continued until or unless one of them eliminated the other one. This battle can be represented with the help of system of differential equations also. So suppose we have these two opposing forces and we represent the fleet A with initially A naught ships and fleet B initially with V naught number of ships. Since the losses for each fleet will be proportional to the effective firepower of the opposing fleet, mathematically we can write down in the form of equation number 10 and 11. And here it is assumed that effectiveness does not change throughout the battle, so that the rate at which a navy loses ships is proportional to the number of ships in opposing fleet. So these two equations indicate that the rate at which one navy loses ships depends on only two things. The first thing is the number of ships in the opposing fleet, and the second one is effectiveness of the opposing fire. So now we want to know that if the two fleets are equal in the battle, so that means if they are equal, that means A and B, they are equal. So we, let us say we take some constant value, say it is K. So what would be the effect on the number of ships still fighting in the battle? So if we add these two equations, if we add them, so adding, we get equation number 12 of the form. So we reach to this expression, and it will show that the total number of ships in the battle decrease exponentially over the time of the battle. On the other hand, here we added them, and we got this result, and in case we find the difference between the two, so if we subtract, then we reach to this conclusion, and it will show that during the battle, the difference in the number of ships that remain in the winning fleet A and those remaining in the losing fleet B increase exponentially. So we can also find the expected number of ships remaining in a particular fleet when the other one is eliminated. So let us say B is eliminated. So that means we will put B is equal to 0. And we know that the expected number of ships remaining in fleet A. So we will use the initial condition, and we reach to this expression that is given by equation number 16. And the value of A is given by this quantity. So this is the number of ships in fleet A at the end of the battle. And in continuation to this, there was a principle of concentration. So according to the principle of concentration, by focusing on one portion of the enemy and destroying it completely, a force can win the war even if its initial strength is low, which is not the case in direct one-to-one combat. We saw earlier also. So it want to say is that if one force can concentrate its entire strength on a particular portion of an opposing army and destroy it, it may then be able to attack the remaining portion of the opposing army with its remaining strength. So Lancaster believed that air power would be so effective because of this. So an air force can be deployed in full force against selected portion of an opposing army. And we know that Lancaster assumed that the combat between two homogeneous forces under modern conditions could be modeled by these two equations we saw earlier also in the square law. So we can use them again. And using the square law and the previous equations, we can extract the expression for R and B. And let us see with the help of an example that how it is working. We saw that instead of using the full number of army men, it can take a part of that also. And see, suppose we are having the information, and the attrition rates that we took as constant. So let us say they have taken to be as 0.1, both have 0.1, and we do have some initial value of red army and blue army. So let us say right now we are having 60,000 army men in red army, and in blue army there are 50,000. Supposing that force B attacks on only 30,000 soldiers of the force R initially, so we divide it as a mini combat 1 and mini combat 2. So total number of army men in Red Army are 60,000. But in the first mini combat, we see that only 30,000 take part. So 30,000 are still left here. So when Red Army men are 30,000 here, and from Blue Army they are 50,000, they take part in this battle, and it continues. Thus, for the winning condition of B, clearly we need this inequality to hold, and we are having R is equal to 0. That means we will get the time T as 6.93 units. It depends on our modeling that what units we are assuming, whether it is in terms of years or something else. So the number of B soldiers surviving in first combat is 40,000. And so the remaining 40,000 soldiers from Force B now will fight against the 30,000 soldiers of the Red Army that they were left over. So in the second mini combat, it was the first mini combat where 30,000 army men from Red Army were engaged in the battle, and for the remaining 30,000 in the second part of combat, remaining 30,000 are here. And again, we have assumed the attrition rates A and B as constant. So the condition of winning of B is this inequality shall hold. And if we put R is equal to 0, we get the time T as 9.73 units of time. That is approximately 10. So force R gets annihilated. And number of B soldiers surviving in this combat is given to be as 26,548. So, to understand the overall picture of such models, we can also have the phase plane analysis. So, let us see the picture of our phase plane analysis. I hope students are already familiar with the phase plane analysis, when we can solve the given system of equations with the given initial conditions and values of all the parameters corresponding to different values. We will get infinitely many solutions for the system. But a model is formulated and solved to answer some particular questions. So for this purpose, we need to analyze all these infinite number of solutions. So phase plane analysis will help us to understand the modeled phenomena. So we see that we have the Lancaster's model with aimed fire is given by the system of equations, and the equilibrium point, the only equilibrium point is 0, 0. So we will see what is happening. We see that the dr and dt, that is rate of change of Red Army and Blue Army, both are negative, and R and B are positive. So both R and B are decreasing. So this direction of both R and B is decreasing. So here we are representing the Red Army, here is Blue Army. So their direction is depicted with the help of negative direction. So the resultant direction is towards 0. So it is shown. And to sketch the trajectories, we need the turning point. So for the turning point, we will put dB upon dr to 0, and it will give us that r upon b into r upon b is 0. But we know that small r and small b, they are representing the attrition rates, and capital R and capital B, they are the red and blue armies, and they all are the positive quantities. So this means it can't be is equal to 0. So no turning points are there. So since dB upon dr is always positive, and B is an increasing function of R. So to observe the behavior of B for large value of R, we find the value of B. And so we get the equation of straight line. So it is being represented here. For very large value of R, a small quantity K will contribute nothing. So we can neglect it also. So that is, it is moving towards infinity. So it will look like a straight line. So to find the B intercept and the R intercept, we put R is equal to 0 and B is equal to 0. So we have B will cut the axis when K is 0. K is greater than 0, and R will cut the axis when K is less than 0. So since the direction vectors are decreasing for K greater than 0, as we increase the value of R, it will be asymptote to B is equal to R upon B root R. So we have represented these asymptotes. That would be the condition when B wins. And if R naught B naught is the initial condition, we will move towards B axis and will stop at root K. That is at the stage when number of soldiers in Red Army is 0 and B army wins. So for our army to win, that means Red Army to win, for K less than 0, we will move towards R axis and will stop at a negative of B upon RK, where B is 0. So that is the number of blue soldiers is 0. So we can this way analyze our model of war also. Though we studied so many advantages, and we saw that how we can solve these models considering certain assumptions, but still there are some drawbacks that we can see, that like other mathematical model, Lancaster's combat model is also having drawbacks like constant attrition rates. We saw that whether we took small r and small b as attrition rates, they will always taken to be as some constant quantities. But actually, in real life applications, when we will have to study some battle model, they may not be constant. So it is one of the biggest drawback of this model. And also it talks about the homogeneous forces, that both the forces are homogeneous, but it may not happen actually. Also, non-combat losses such as surrenders and desertions, etc., are not considered. So there can be many more parameters also, but they have not been included. So beyond Lancaster's linear and square laws, we will see some modified models also. So let us say now we see there is some mixed combat. That means both the forces are not alike. Like we saw in the previous cases, there is red army and blue army. Now in case of mixed combat, both of them cannot be of same type of armament. So in this particular model, we considered that the second one is the guerrilla force. So the losses to the guerrilla forces are proportional to both the number of conventional force and its own numbers. So now we see that how this model will be modeled. So since here we can see that if X is the guerrilla force, X is representing the guerrilla force and Y is representing the conventional force. Okay. So since guerrilla combat loss rate is proportional to the number of guerrilla and conventional encounters, whereas in case of conventional combat loss rate is proportional only to the number of guerrillas. And again, small a and small b, they are the constants representing the combat effectiveness of each other. And the guerrilla force is largely or entirely organized in small units that are dependent on the support of the local population. Tactically, the guerrilla army makes the repetitive attacks far from the opponent's center of gravity with a view to keeping its own casualties to a minimum. So this may provoke the enemy into the brutal, excessively destructive response, which will both anger their own supporters and increase support for the guerrillas, ultimately compelling the enemy to withdraw. So this may happen actually. That's why the opponent is changed here, and we have taken into consideration this mixed combat. And if we solve these two equations, so we will reach to this result, and from here we can draw some conclusions and we can extract the value of y. So we have extracted the value of y, which will give conditions of winning force for each other. So we can see that conventional force gets annihilated and the guerrilla force wins under this circumstance, and the guerrilla force gets annihilated and the conventional force wins when this condition is true. And if there is equality, then that means the forces annihilate each other. So similar type of models and similar type of modifications we can see in our models. So it was the some basic assumptions that were considered to formulate and to solve these models. Otherwise, if we have our own objectives, we can formulate our own models to achieve our targets. So here are the suggested readings that were taken into consideration for this. And in case you further need to discuss something, so here is my email ID. This is all, right? Thank you so much, sir.
Ma'am, hello, ma'am.
Hello, ma'am.
Like the present model talking about war and combats. So, like when you talk about a particular population, so I mean this question is just out of context. Like how many soldiers or how many people will be alive? This also depends on the food supply and all other factors also. जिससे war आगे बढ़ जाएगा तो supply कम होगा
Ma'am,
that
your voice is breaking. Your question is not audible. Better if you can write it, because I am not able to understand few words from your sentences.
okay ma'am, am I audible clearly now?
You are audible, but at some times your words are breaking. So
Okay, I think it is because okay, let me write down.
you can write down. I could
Yeah.
guess that you are asking something from the population model, but rest of the sentence was
Yeah,
not.
ma'am. Actually, I was just saying, like, say, we are taking the case of a war combat. Other than war, I mean, soldiers can also die due to lack of food facility also. Right?
Exactly. This is
Yeah.
what we discussed in the drawbacks of Lancaster model, that
Yeah.
many parameters were missed there. Some of them may also surrender.
Yeah, ma'am. Yeah,
Like there
yeah,
can be many possibilities. So
yeah.
when we are constructing our model, we
Mm.
need to take care what parameters, what assumptions we are making, what is the focus of study. So it is
Okay.
all depending on us when we are formulating our model.
Okay. 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 Thank you, ma'am.
Welcome, ma'am.
I don't think any other questions are there. So thank you so much for your nice presentation, Dr. Dhawan.
Thank
And
you.
I request our Dr. Abhijit to offer the vote of thanks from our department as well as from this university for your nice presentation. Dr. Abhijit. Thank you, Dr. Sharanjeet Dhawan, and thank you, Abhijit.
Thank you so much, ma'am. I'm also really thankful to you, all of you. You gave me such a wonderful opportunity that I could discuss some of my viewpoints. Though there can be many other models, it is such a vast area, mathematical modeling. You cannot discuss all the models. So I just wanted to, bring some of the models. They should not be boring for the students, but at the same time, they shall be able to understand how we are, enriching our knowledge in the field of mathematical modeling. So this was my main objective.
Right. Right.
So, ever there is any opportunity for me, I would be happy enough to serve for the institution. Thank you so much. Thank you all.
Definitely, we inform you in
Yeah, sure,
future.
ma'am.
Thank you.
Sure, ma'am.
Thank you so much.
Thank you, ma'am.
Dr. Dhawan, recently, in the coming March, we are going to conduct the international conference.
Okay, madam.
So if you want, you can join over there and you can contribute your paper also there.
For sure, ma'am. I'll
Yeah.
request Dr. Amit to be in touch regarding
Yeah.
that same.
He
And
will send you the brochure, etc.
yeah, sure,
And
madam.
yeah, thank you.
Thank you so much. Thank you, everyone.
Thank you, everyone. Thank you.
Thank you. Okay, sir. Thank you.